Welcome back to another explainer. So, if you're the kind of learner who loves uncovering the hidden mechanics behind how we actually understand the physical world, well, you're in exactly the right place. Today, we're diving deep into these fascinating, mostly invisible systems that we use to measure reality. It's a field known as instrumentation and control. I mean, think about it. We trust our speedometers, our thermometers, our digital scales completely every single day. But how do they actually capture truth from the physical universe? Let's get right into it.
To kick things off, I want to frame our entire discussion around this incredibly profound quote from our source material. In nature, whatever exists, exists in some amount. I just love that because it brilliantly illustrates that measurement isn't just some dry, boring engineering task, right? It's literally a fundamental truth of the universe. Humanity is constantly trying to quantify our world so we can actually understand it, design better technology, and, control our environment. Measurement is, for all intents and purposes, the ultimate bridge between physical reality and human knowledge.
And to help us get across that bridge, here's our roadmap for today's explainer. First, the art of measurement, then the anatomy of an instrument. Next up is the quest for truth, followed by judging instrument performance, and finally, we'll wrap up with the anatomy of error. All right, let's jump in.
Section 1. The Art of Measurement. Categorizing the tools of the trade. At its absolute core, measurement is really just a quantitative comparison. You're comparing a predetermined standard with an unknown magnitude. But before we even start looking at the instruments themselves, we have to know what we're actually looking for, right? Enter the measurand. This is the core term you've absolutely got to know today. The measurand is simply the unknown quantity or variable that we're applying to our instrument. So it could be temperature, pressure, flow rate, voltage, you name it. The entire job of any measuring system is to capture the true value of this measurand as faithfully as humanly possible.
So how do we actually capture it? Well, we've got different categories of instruments, and they really highlight the built-in trade-offs of physics. On one hand, we've got mechanical instruments. Think of your heavy, rigid, old-school tools. They are incredibly reliable for static, unchanging conditions. But because they have physical mass, they suffer from high inertia. They literally just cannot react fast enough to rapid, dynamic changes. On the flip side, we have electrical instruments. These use electrical methods for lightning-fast detection. The catch? Historically, they still had to rely on mechanical pointers or meters to actually show you the result, which, as you might guess, dragged down their overall response time.
And that naturally brings us to how the data is actually represented. Analog versus digital. Analog instruments represent physical variables as continuous, smooth, stepless variations over time. It's kind of like the sweeping hand of a classic clock or an old analog speedometer. But digital instruments, they represent variables in discrete, finite steps. Now, why does this matter so much? Because jumping in those discrete steps makes digital signals highly immune to background noise during transmission. Plus, it makes them absolutely perfect for feeding directly into modern computer processors and automated control systems. It's a real game changer. We can also categorize things by how the instrument finds its balance. Let's look at deflection versus null type instruments. A deflection instrument is a lot like that spring scale at the grocery store. The measurement pushes or pulls a physical element, actually displacing it to give you a reading. It's simple, it's quick. But a null-type instrument operates entirely differently. Picture an old-school equal arm beam balance where you keep adding weights until the pointer hits absolute zero, or null. Now, while deflection types are definitely simpler and respond a lot faster, the crucial takeaway here is that null types are often way more accurate. Why? Because they don't interfere with the state of the measured quantity to nearly the same degree. Section 2. Anatomy of an instrument. The journey of a signal. You see, a complex instrument isn't just some single magic box. It's actually a beautifully orchestrated system. Whether we're talking about a massive industrial flow meter or just that digital kitchen scale sitting on your counter, every generalized measurement system follows 4 critical steps. Step 1 is the primary sensing element. This is where the instrument physically meets the measurand. Step 2 is variable conversion and manipulation, which is just a fancy way of saying that the physical reaction is turned into a workable signal, usually electrical, and maybe it gets amplified. Step 3 is signal conditioning. This filters out all the messy noise and shapes the signal. And finally, step 4 is data presentation, where the data is translated back into something human readable, like on a screen or recorded by a computer. So, if we look at the block diagram mapped out for this process, you can actually follow this transmission path perfectly. The physical quantity enters on the left, hits that primary sensing element we just talked about, and then travels through transducers and amplifiers. And right in the middle, you've got that signal conditioning box. That's absolutely crucial because that's where filters remove interference so the true signal doesn't get distorted. Finally, it arrives on the far right at the data presentation element, like an analog indicator or a digital display. It's basically a highly coordinated relay race of data. Let's ground this abstract concept in reality for a second. Take the Bourdon-tube pressure gauge, a super common mechanical instrument. So pressure enters the curved Bourdon tube, which is our primary sensing element. As the pressure builds up, the tube actually tries to uncoil. That tiny little displacement, that's our variable conversion. But, you can't easily see a millimeter of uncoiling with the naked eye. So a mechanical linkage and gearing arrangement step in as the variable manipulation element. They amplify that tiny movement into a large, easily readable sweep of a pointer on a dial, which is our data presentation. It maps perfectly to the generalized system we just went over. Section 3, the quest for truth, establishing standards and calibration. Now here is the million-dollar question. How do we actually know that our pointer, or our digital thermometer display, is telling us the absolute truth about the measurand? Well, the answer is calibration. Calibration is literally the ultimate anchor of all measurement. It's the process of rigorously checking an instrument against a known standard of much higher accuracy. We rely on this strict, cascading hierarchy. We have highly protected primary standards kept in absolutely pristine conditions, and those are used to calibrate secondary standards. Those secondary standards are then used to calibrate everyday working standards in labs and factories, which finally calibrate the instrument you're actually holding in your hand. This unbroken chain is the whole shebang. It's what gives a measurement its actual meaning. And when we do calibrate, we create something like a static calibration curve. Just picture this plotted out on a graph. Down on the horizontal axis, we've got the known input values from our trusted standard. Over on the vertical axis, we have the actual output our instrument gave us. By plotting these points, we draw a curve of best fit. This curve establishes the fundamental logic for the entire instrument. It essentially tells the system, hey, if the sensor outputs a 4, the true input was actually a 2.5. It acts as a translation dictionary between the raw output and verified truth. Section 4, judging instrument performance, defining good measurement. Once an instrument is fully calibrated, we really need to analyze the static performance characteristics. These dictate what an instrument can do, and crucially, its limitations. And one of the most fascinating limitations is something called hysteresis. Imagine pushing a heavy box forward and then trying to pull it back. Because of friction, it takes completely different amounts of effort, right? Well, instruments experience this exact same thing. Hysteresis is the non-coincidence of loading and unloading curves. So if you slowly increase the pressure on a gauge up to 50 psi, and then later you slowly decrease it from 100 psi back down to 50 psi, the gauge might actually give you two slightly different readings for that exact same 50 psi mark. No way, right? But it's true. This is deeply rooted in the second law of thermodynamics. There is simply no perfectly reversible process in the universe. Internal friction and elastic lag are always going to cost us a tiny bit of truth. Which brings us to a massive misconception, and frankly, one of the most critical questions in all of engineering. Are accuracy and precision the same thing? We use them totally interchangeably in everyday conversation, but in the world of measurement, they mean entirely different things. Let's break this down using dartboards. If you picture a dartboard where the thrower is hitting the exact same wrong spot over and over again, that is high precision. The instrument is reliably reproducing the same reading. But it has a massive bias error. It's nowhere near the bullseye. So it's highly precise, but highly inaccurate. Now compare that to a dartboard where all the darts are clustered tightly right smack in the middle. That is true accuracy. High accuracy requires both low precision errors, meaning the darts aren't scattered all over the place, and low bias, meaning they are centered right on the truth. So you can definitely have precision without accuracy, but you absolutely cannot have true accuracy without precision. Section 5. The anatomy of error, embracing the flaws. We just have to acknowledge an inescapable truth here. No measurement is ever completely perfect. In fact, categorizing our errors is just as important as making the measurement in the first place. We generally divide measurement errors into 3 main buckets. First up are gross errors. Let's be honest, this is on us. It's human mistakes. Reading the dial from the wrong angle, totally messing up a calculation, or just using the tool incorrectly. Second, we have systematic errors. These are built-in biases. Think of a stretched measuring tape or a thermometer reacting to the heat of the room. They consistently push the reading in one specific direction. The good news, though, systematic errors can usually be calibrated out. But then we have the third bucket, random errors.
These are the completely unpredictable variations and the inherent noise of the physical universe. We can literally never fully eliminate them. We can only use statistics to try and average them out.
And because of those persistent random errors, we have to rely on uncertainty analysis. Honestly, here's the philosophical kicker of this entire explainer. The absolute perfect true value of any physical quantity, it is forever unknowable to us. Since we can't know the absolute truth, we have to statistically estimate a secured interval, a range of probability where we are highly confident the truth likely lives. So we don't just say a rod is 10 centimeters long, we say it's 10 centimeters plus or minus 0.1 centimeters. That little plus or minus right there, that is our calculated uncertainty. And that leaves us with a pretty provocative final thought. If the true value is just a ghost we can never perfectly catch, and every single instrument out there carries its own inherent uncertainty, friction, and error, how close are we really to quantifying the true nature of our universe? Well, it turns out measurement isn't actually about achieving absolute perfection. It's about designing brilliantly structured, continuously calibrated systems that get us incredibly functionally close. It's about embracing the beautiful, complex imperfection of human engineering. Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll see you next time.